In chemical and biological manufacturing processes, alarms are used in multiple ways. Some alarms indicate the status of a particular piece of equipment. For example, an alarm may indicate that a pump is turned off. Other alarms are used to indicate abnormal measurements of process variables. Often these kinds of alarms are coupled to the sensors and transmitters in the basic process control system. In this case, there's a flow control loop with a flow level switch. When the measured flow rate falls below a particular level, the flow alarm low is actuated. While it is often convenient to couple abnormal measurement alarms to the sensors in the basic process control system, sometimes an alarm has its own independent sensor or switch that actuates it. In this case, the flow alarm does not need to know the actual value of the flow rate, it just needs to report that the flow rate is out of range. Other times, an alarm will have a sensor and a transmitter associated with it, so that in addition to indicating that the flow rate is out of range, it can also indicate the value of the flow rate. Safety instrumented systems and emergency shutdown systems are always designed with their own sensors and transmitters that are independent from the basic process control system. When designing alarms, consider that alarms should be used to indicate abnormal conditions that require an operator response. They should be designed with the user, that is, the operator, in mind, and have a priority level. Between 2 and 4 levels is reasonable. Alarms that have 10 levels or only 1 level are not useful. The highest priority alarms should only be used if they are protective or safety related, or if they require an immediate response. Alarms should be designed so that the alarm condition persists until it is acknowledged. And alarms should only be suppressed if there is a legitimate reason and if the alarm has a reminder. Alarms should also have automated logging. The logging is important so that alarm histories can be reviewed to find things like standing alarms and nuisance alarms. Alarms should not be changed without documentation and management of change orders, just like other components of the basic process control system or process changes. Alarms can be avoided by using what are called state-based alarms. State-based alarms are those whose limits change to accommodate procedures such as startup, shutdown, and product and feedstock changes. Using state-based alarms can help to eliminate standing alarms during abnormal operating conditions, such as when a unit operation is being started up or shut down. During abnormal operating conditions like this, many process variables can be expected to be outside of their normal operating ranges. And if too many alarms are being activated all at the same time, it's very difficult to discern which alarms really require a response and which alarms are just being activated because the process is outside of its normal operating condition. When periodically reviewing alarm histories, it's good to look at alarm frequencies. Various trade groups have recommendations for alarm frequencies. For an operator, during a normal shift, they can be expected to deal with something like 144 alarms per day, and no more than 9 standing alarms. Standing alarms are alarms that remain in the alarm condition for extended periods of time. Occasionally, operating conditions lead to multiple alarms simultaneously. No more than 10 alarms should have to be dealt with within a 10-minute interval at a peak alarm condition. And on average, operators should have to deal with only 1 alarm per 10-minute time interval. It's best if the priority distribution for alarms is heavily distributed towards the low end of the priority range. So if alarm priorities are low, medium, and high, maybe 80% of the alarms that an operator might deal with in a shift should be low priority alarms, and only 15% should be medium priority, and only 5% should be high priority. When reviewing alarm histories, it's also valuable to look at the alarm rates during upset conditions. During upset conditions is when the most alarms are usually activated, and also when it's most important that an operator can discern which alarms need the most immediate attention. Finally, when reviewing alarm histories and logs, one should look for alarms that can be identified as bad actors. Bad actors are individual alarms that account for a very large fraction of the total number of alarms. Here's an example of an alarm frequency distribution, reviewed over an 8-week period. Over 8 weeks, this one level alarm was activated over 3,000 times. The next most frequent alarm was a flow alarm that was activated almost 3,000 times. Collectively, the top 10 enunciated alarms accounted for 55% of the total number of alarms in that 8-week period, and 40% of the total number of alarms were caused by just 4 alarms. By taking a closer look at the operating condition that led to many of these alarm events, it may be possible to identify one or more of these as a bad actor. Perhaps bad actors could be redesigned or replaced with state-based alarms. In the next video, we'll show a typical type of calculation that's used to design an alarm.